When finding extrema in motion situations, you do it identical to how we did before. So we'll simply be looking for the critical numbers or endpoints of an interval. Now, as a reminder, critical numbers occur where the derivative is equal to 0 or undefined. So whether you're doing things analytically or graphically, we're just going to look for where those critical points happen and then examine the values, and who's ever the biggest will be the max, who's ever the smallest will be the min. So our first example, we'll do analytically. Here we have the position of an object along the x-axis where, we're going to be measuring it in feet and time in seconds. So what we want to first look at is what's the maximum distance the particle travels from the origin. Now, as you can see, we are in a closed interval, so we'll have to examine, the endpoints of 0 and 2 for the time, but we also want to look at any critical numbers, which means that since we're looking at the maximum distance, it is the maximum of s of t. So its critical numbers will happen where its derivative velocity is equal to 0. So the first step is, let's calculate what the velocity of this is at any given time. So that would be equal to negative 32t plus 48. Now to find critical numbers, we'll simply set this whole thing equal to 0 and find out where the velocity equals 0. And we see what happens when you solve for it at time equals 1.5 seconds. Now remember, because we're on the closed interval, we're not just going to check the critical number, but also these endpoints in the position, because we're trying to determine where the maximum distance is, and that would be a position situation, because obviously we're going to compare that value to where the origin, 0. So we're going to ask what the position is at time 0, and we'll ask the position at our critical number, 1.5, and then check the last endpoint, our position at time 2. Well, at 0, when you plug it in, we get a value of negative 8, meaning it's 8 to the left of the origin. Now, when I plug in 1.5, we'll get an answer of 28, meaning it's 28 feet to the right of the origin. And then when I plug 2 in, we'll get an answer of 24, which of course means it's 24 to the right of the origin. And since we're looking for max distance, this number is right here. So that means 28 feet is the maximum distance that the object is from the origin. Now, another question they could ask is, what's the maximum speed? Which means that we're looking to maximize speed, or our velocity equation, so we'll have to figure that out and then kind of work from there. Now, from before, we already noticed that the velocity at any given time was negative 32t plus 48, but when you look at its derivative acceleration, it's constant. It's just a negative 32. Now, what that means is that there's no critical numbers, right? There's no zeros for acceleration. So what we can do then simply is to look at the endpoints, because those will be the only places where you might have a maximum speed. Now remember, since we're calculating speed, we're going to look at the absolute value of the velocity at these points. Okay, so we'll check the first endpoint 0.5 and the other endpoint 2, because again, there are no critical numbers. Now looking at the absolute value of the velocity at time 0.5, it has a value of positive 32, of course. And the absolute value of the velocity at time 2 is going to be 16. And since we're looking for the maximum speed, this it is right here. So our maximum speed is at time, 0.5 seconds, and is 32 feet per second. Now let's look at a rectilinear motion question numerically. So we'll be looking at tabular data, right? Points at certain spots, and that's all we know. So without a function, we have to slightly adjust how we do our work. So in this table, we have the time in seconds, and at those specific times, we have velocity in meters per second. Okay, and it's going to be going for the interval from 0 to 12, so we're going to stay within this. Now, the first question we're going to be looking at is, when is the object at rest? Well, remember, when we talk about being at rest, that just means that the velocity equals 0. But remember, because we don't have a function, we may not be able to specifically say when it is. And that's kind of why they worded it, is there a time? They're not looking for that specific time. So we have to kind of look at the evidence in front of us and say, well, maybe I can't tell you exactly when it stops, but I can kind of give you an idea of when it happens. Now, what I notice about the graph is that the velocities, you can look at the values as we move along, change from being positive values to negative values, which means at some point in time, between time 5 and time 8, there was a spot where the velocity had to equal 0. Because remember, this is a differentiable function, so we know it's continuous. So obviously, if we had a positive values and then negative values, there was some instant in time, I don't know exactly where, but somewhere between time 5 and time 8 that it equals 0. So we would just say, yes, that'd be the case, and the explanation, of course, would be some time between those two time periods. So we just say between t equals 5 and t equals 8 seconds. Now, of course, the explanation that you would write out would be because the velocity changed sign. Now our next question asks, at time 8 specifically, is the object moving to the right or to the left? Well, clearly we do know about time 8 since that's our table, and because the velocity is negative, we can easily say that the object is moving to the left. And again, our explanation would be because the velocity is negative. Now, for our last question, we'll look at a very common AP style question, something they ask a lot on AP exams. Here, they're asking us to approximate the value of the derivative of v at 10. Now, remember, we don't know the derivative of velocity, nor do we know anything about the time 10. But in order to approximate the derivative of velocity, we simply have to remember that this is approximating the rate of change of velocity. And remember, to find the rate of change, what we can do is we can assume that 10 is right here in the middle between these two values. So if we just do the average rate of change, that can give us an approximation for what the instantaneous rate of change may be. Now, of course, it's not going to be perfect, but because, again, 10 lies in between these two, we can switch out and say, well, I don't know the instantaneous, but using the average rate of change can give me an idea what that looks like. So essentially, given these two ordered pairs here at time 8 and 12, we're simply going to find the slope. So we're going to approximate the instantaneous rate of change of the velocity at 10 by looking at the rate of change, right, from 12 in the velocity to 8. And that would be, of course, over the time period 12 to 8. And plugging those numbers in basically gives us negative 150 minus negative 120 divided by 12 minus 8, which is 4. And when you simplify that, we get an answer of negative 15 halves. So that's an approximate value of the rate of change instantaneously at 10. Now, of course, they do want us to indicate our units of measure after we've shown our work here. And because this is the rate of change of velocity, that means that it will be not just meters, per second, but meters per second squared.